Hello everyone. As usual, we'll start at around 11:10. Hi, everyone. We'll start in about a minute. As usual, please, if you can turn on your camera, please do so. It helps me a lot. Thank you. Okay, let's start. So today we're in week 8, which includes the reading week. And today we're going to talk about processes again. More specifically, we're going to focus on the storage thing. So last time we spent a lot of time, on the arithmetic unit. And today we're going to spend the whole lecture, the whole 2 hours, talking about how we're storing data, right? And we're going to get at very low level. We're going to talk about registers, caches, even DRAM a little bit. And then at the end, I'm going to show you a little bit how the cache operates. Again, I cannot cover that too deep. That's usually covered in more advanced courses later on. But I hope you're going to get a sense on how difficult is the problem of building efficient caches. Okay. Again, I'll repeat my request. Please, at least some of you turn on your cameras, because I feel like I'm talking to myself if I don't see anyone. Okay. Can you hear me at least well? Okay, good. So this is a super simplified version of the microprocessor, and there is an arithmetic unit that we spend a lot of time. There is a storage unit and the control unit, and today we're going to talk about storage unit. So we learn a lot about arithmetic thing as of now, right? And that's been quite, hopefully you learn a lot. You understand how these things now operates, with a very good granularity. We know we can do addition, subtraction, logic operations. All of this can be done by our LU units. We studied it carefully, how exactly it does different operations, how it does it efficiently. All that was covered. But obviously, when we do arithmetic unit, one question comes is where those A and B are coming from. So those parameters inputs are stored somewhere. They're coming from where they're not coming from nowhere. And the results also need to be stored somewhere as well. It's not necessarily goes right into another compute unit. So this is what we try to answer today, the storage thing. We're going to talk about register file and the main memory and all their optimizations like caches to it. So this is something I added to this slide deck, is from a very high level, from the von Neumann model, essentially. What the memory means for you is some abstract thing where you can load the data from and you can store data to. And this is at a very high level picture what the memory is, right? So there is an API in all the languages, including low-level languages like assembly that you're going to learn soon, that has this API that allows you to talk to memory by sending load instructions to read from it and store instructions to write to it. Obviously, it's not organized as a primitive homogeneous thing. It has multiple layers. It has a hierarchy, which we typically in computer architecture call memory hierarchy. And as my specialization is computer architecture, obviously this is something I can go a little bit deeper than on other topics to give you a sense on how the this area looks like. Okay, so I guess there is a lag sometimes again. Okay, so essentially, just to repeat myself, we're going to talk about computer memory hierarchy, and different layers of the memory hierarchy are sorted by access speed. So there are registers which are in the processor themselves, right? And this is as fast as it can be, and it typically operates at the speed of LU units, so we don't slow down the LUs by supplying it with the register fast. Like every time you do an add, you don't want to do an add in one cycle and wait for 5 cycles until the inputs arrive. That would be meaningless. Then there are several levels of caches. I hope most of you have heard that existing processor has caches, right? One thing I want to highlight that sometimes students don't understand, cache is actually not a requirement. So cache is an optimization. I can completely disable cache and my machine's still supposed to work. It's going to be significantly slower, but it will still work. So it's hard to imagine machines without caches right now. Most processor has them, but remember, this is an optimization. So cache might have several levels. The closest is next to the processor, L1 cache, right? And there are 2 types, one for data, one for instruction. Again, in the future courses, if you get interested in computer architecture and you take one of these courses, you're going to learn about that much more. And there are hierarchy after that. And then there is a memory. And memory, that's not an optimization, it's a requirement. It's having something like DRAM or some other technology that implements main memory, that's a requirement. You cannot have a von Neumann model operate without that. Then there is memory that is typically off chip, but it's not. It can be on chip as well sometimes in some smaller devices. And there is hard disk for virtualization, requires OS support to access. And when I say hard disk, I also mean SSDs, right? Like if you use non-volatile memory, or sorry, not non-volatile memory, but if you use flash, right, for example, and a lot of modern laptops has flash instead of magnetic drives, but they all operate as in the same principles. From the OS perspective, there's not big difference between flash versus hard disk, right? This is where everything is backup. And for a very long latency and something that is outside of your machine, that we have network, and this is typically not for process execution. This is something just to read data from some far apart land. So the best way, there are different analogies you can make about memory hierarchy, but if you, I guess we're approaching the lunchtime soon, so hopefully you're not too hungry, but if you use a data analogy here, so registers, this is a plate in front of you, which a lot of you might consume while I'm talking, I'm pretty sure. So this is register, this is right in front of you. Your cache is that your fridge in the kitchen, essentially. Memory is the grocery store downstairs. Hard disk is the farm in the suburb, but you can go occasionally for some special foods. And the network is the farm in a different country. So this is roughly the latencies and the differences in how long it can take. Another analogy you can use is a bookshelf that is right in front of you, books in your table versus a library versus the library in your local area versus your city versus their Congress library in US or something like that. So this is the typical analogies that people use. Okay, so this is how it looks conceptually. What we're going to learn today is how it's actually used. So essentially, there are units in the CPU that store multiple data values that can be used by the CPU. And registers, as you can imagine, they're the fastest, but also because they're the fastest, there are way fewer of them, because to make them fast, you need to sacrifice something else, right? So if it's very fast, it means it's more expensive, right? So you only had a handful of them. So the typical CPUs that you're going to deal with in the near future is going to have either tens or maybe hundreds of those. GPUs are different. We're not going to talk about accelerators for now, but the typical thing you had to deal with is going to be on the order of tens or hundreds. So it's a small number of fast memory units that allow multiple values to read and write to memory simultaneously. The main memory is much larger. It has tons of memory cells. I'm going to cover that in some details later on. And they used to store the main information to be processed by the CPU. It stores the whole working set essentially for this data set. Because if it's not, then your your application is probably going to work very slowly. Because if you're going to permanently go to disk, it's going to be very slow, right? Okay. So where are those magic things are located? So at a very primitive way to think about it, your registers are inside of your CPU, right? Literally inside of this thing. Your memory is this chip that if you ever, hopefully ever open your desktop, if you had one, or if you look at someone else's desktop, those are those, you know, chips, DRAM chips, that's how they usually called. By the way, memory doesn't have to be necessarily use just one technology. This is the most dominant technology used right now. And for the last 30 years, it's the most dominant technology. Registers are here, cache is also here in most cases. Okay, this is how the typical motherboard gonna look like. And remember, this is going to be a cheap, tiny chip there. Registers are in here in the CPUs, right? This is AMD chipset. And the memory chips are going to be plugged in here. And that's how you get memory. So you see some of them are filled in, like this guy, and there are empty slots. So those are the slots we can plug in extra memory, right? And you know, the memory typically on your typical desktop varies in gigabytes, right? While the registers are really just tens or hundreds of those. And cache is typically in megabytes. So you see the difference in capacity. And I'm not going to talk about latencies too much here, but that's something you can learn in more advanced courses. So I see a question. Cache is also in CPU, right? So Quintan is asking. So the very short answer, mostly, right? So I remember I said there are multiple levels in the hierarchy. There's L1, L2, L3. The bigger the number, the further away from the CPU you are, it becomes bigger. So on pretty much everything you use, right, on a standard machines, it's on chip, right? It's always there. But there are big mainframe machines that say companies like IBM are building, and they have 5 or 6 layers of caches. And they might have caches that are off chip, but that's more like an outlier. For most cases, you're going to see caches on chip and memory is off chip. Any questions about that? That's still very high level, but I want to understand where those things are physically. So if register that makes the PC faster and hard disk is much further, then why switching from hard disk to SSD makes much more different than switching a CPU? Excellent questions by Jonathan. So essentially, why do we ever worry about switching to from hard disk to SSD? And there are multiple reasons. So there are, someone already started to ask about moving parts of hard disk and the fact that hard disk is less reliable. You can argue about that. Flash has also reliability issues. If you ever use like small flashes for a long time, you see they're also gonna get broken parts of it, right? Broken cells. But the real fundamental reason is because it's not like you always run a small application. There's a whole operating system running. And from the user perspective, there are a couple of benefits. First of all, when we all turn on our machines, we really don't like to wait a minute or even 2 minutes until it turns on. We want to start it faster. So if you ever try using older hard disk machines versus newer generations of machines with SSDs, you're going to see a huge difference in boot time, right? That's one thing. Also, when you manipulate with large files, right, it's not about your code running your tiny application. That's not going to benefit much. But if you're going to copy a lot of images or video files, you're going to see a huge difference in terms of time it takes to copy over. So the question, has SSD has better random reading performance? It's a little bit questionable. SSD is in general faster for both reads and writes than hard drives. So another question by Terry Wan is, why not have a ton of registers instead of having to use lower types of memory in the hierarchy? Very good questions. The best way to think about it is this small register, small number of registers. They takes a lot of area and a lot of power. So to make them fast, I need to have a design that's going to be very costly. So when I'm going to talk about SRAM versus DRAM today, you're going to see that SRAM design has no capacitor. So because it doesn't have capacitor, it has to compensate for that for having many more transistors like inverters, and that makes the cell bigger and more power hungry. So essentially, the short answer is you can have a lot SRAM as well, but the larger SRAM becomes, the slower it becomes. So there are two factors. First of all, SRAM is more expensive than DRAM. SRAM is a technology that I'm going to describe today that is used for both registers and caches, right? And DRAM is used for main memory. But to answer the questions, why not having just tons of registers? So they're very costly, they're very power hungry, right? And the more you have of them, the slower they become. I know it doesn't sound intuitive right now why they would become slower, but the problem is that you need to access them. Later on, I'm going to show you the flow of accessing cache, and you would understand that the bigger it becomes, the slower it's, even with the same technology. So there is no like a silver bullet here, so I can get both the smallest and the fastest and the cheapest at the same time. Did I answer all the questions, guys, who asked questions so far? Okay. Assume it is. Yeah, so let's keep moving. So essentially, this is a very schematic diagram to show the processor. And you see there are registers here, right? That's the memory part. So this is the register. If you look inside the CPU, they're going to be part that has registers, right? There's LU units, there are registers. There are part that connect you to caches. There is a code cache and data cache. And there is a part that connects you to RAM, right? But the RAM is off chip. And this is the whole core, right? And there's execution units, all this other complexity. Okay. Okay, let's talk about register file. So the register file is just an array of registers in the CPU. And the way it's stored as a, essentially an array. And you had a way to read and write from it. You had different parameters. So like the parameters is whether you want to read or write, what is the destination register number, and then there is a data to write if it's a store, and there are two registers, A and B, that you can give and the values you can get out. So you get the address and of the register, and you get the value from the register out of the file. As you can imagine, if you're going to make the structure larger and larger, it's going to be harder and slower to index in the hardware. So the bigger it is, the harder to index, the bigger the latency. It's not impossible to solve, but it's not for free. Okay. Okay. So typical setup, like the most simple, I wouldn't call them primitive, but the most simple processors, like MIPS processors, they had 32-bit registers, and like a typical chip has 32 registers total, and all of them use 5 bits. And you can guess why 5 bits, because that's how many bits I need to address the right registers, right? Okay. So we register file, we need to have a read and write operation. So this is a very schematic implementation of a register file with just 4 registers. So as you can see here, there is a part that enables the write, right? So this is the part that, loads the values into the registers, right? With some decoder that decides which registers to put it. As you can understand, the more registers I had, the bigger this decoder is, right? It starts to add to latency, right? So if you tell me, give me a gigabyte of register, the decoder would be humongous. You already played with one decoder, right? Like one of your, assignments, right? Labs. And you understand building this at that scale won't be easy. The read operation is going to be the other part, right? So this is where you take the values from the registers, and then it goes into their A and B, and there's a select logics to take which values we need. So this is a schematic implementation of the register file read and write operation. So there, essentially, there's a signal that tells us read or write. Decoder can be implemented differently, not necessarily demax. It can be more complicated than that, but in the simplest version it is. Okay, this is a register file. I hope you already get a feeling why you cannot, even using the same technology, why I cannot easily make it super large. It's not a trivial task. So essentially you make it large, the latency will go up, right? And that kills the whole purpose. So we have 2 output because there are because we had 2 parameters, right? And there sometimes we write into one, sometimes into the other. So the typical load has just 1, but there might be some other flags, right? Okay. There can be some side effects. Okay. when you're going to learn assembly, you would understand why sometimes you had a second output. Okay, the main memory, an array of memory units. So essentially the electronic memory is like register files, but the main memory is made up of a decoder and rows of memory units. So, so essentially the best way to think about memory organization, which again, this is a basic class. I cannot go into very low level organizations of the DRAM, but the best way to think about it, if we want a lot of memory, it better be cheap, right? Because we want to get a lot of it. And it means I need to make some sacrifices in terms of efficiency. So I want to make all cells really small and the overhead of handling each of them minimal. So if you look here, for each register, I need tons of circuitry to deal with that specific register. You see how many wires I need, right? For memory, instead of having all the individual wires for every cell, right, as a single bit, I stored them in big chunks, like say 8 kilobits, 8,000 bits, right? And then we access them and select them afterwards. So essentially, you make them very small, and the processing logic, the decoder and the data read is going to be shared. So when I read the data from DRAM, I really have the decoder and everything that optimized to read one single row, 8 kilobytes at a time, but not the whole memory, right? That's going to come with significant latency, but I can get more of it, right? Otherwise, I wouldn't get the density needed to have a lot of memory. Any questions here? So this is the trade-off you frequently had in our computer architecture design. You cannot get the speed and the density all at the same time. Any questions? Okay, let's gradually to move on. So these lines here are used for both input and output, and they're called the bus, and we're going to talk about that. So essentially, the decoder takes into the M-bit binary address and activates a single row in the memory. So this would be, their, truth table for the decoder. So it's essentially it activates one particular row at a time. Okay, controlling the flow. So to control the flow of the executions, because some lines or buses, that's how we're going to call it moving forward. So the question is, can we access one row at a time? It's a good question. And for simplicity, you can think, yes, there are some optimizations around it, but usually when you had one DRAM chip, you can only accept one row at a time, unless there is some fancy optimizations going on. It's called active row, right? If you're ever gonna, do specialize in systems or architecture, you're gonna learn some tools that gonna tell you when you analyze performance of your applications, they're gonna show you how the memory behaves, and it's gonna tell you whether you hit into the same row versus you doesn't, and that relates to something called locality. We're gonna talk about locality in today's lecture as well. So if you write a good code, it might mostly access that one active row, and that's much faster than accessing random rows. So in general, if you write a code that goes through an array, and if you go sequentially through an array versus you go randomly through an array, there's a huge difference in performance, right? Random accesses are more costly. Okay, so coming back to the lecture. So we use both input and output. Since we need that, we want to essentially do both. So we use a tri-state buffer. Remember something we learned before and used in several lectures. So when that flag is write enable and the signal is low, then the buffer output has a high impedance signal, and it's connected to neither high voltage or the ground. So essentially, it allows me to distinguish between writes and reads, right? And that's a schematic table, okay, depending on how the signal is set. Okay, and this is, we've seen before this diagram, so hopefully you still remember. So control the flow using this tri-state buffer is that if you had multiple devices, the control signal C0, C1, and C2 allows us only write into one. So essentially, the best way to think about the shared bus is that only one of the devices can write at any point of time, but multiple can read from different locations, right? So you have that shared infrastructure that had allow multiple reads at the time, but not multiple writes. And usually that's a good trade-off because writes are more rare than reads. We typically read more than write from the memory when we execute the application. So that's typically a very good trade-off. But obviously, if your application has too many writes, then you're going to be bottlenecked by the bus. Okay, so bus at the time can only write one item. Okay, so communication. So what is the data bus? So communication between components take place through this group of wires called the bus. So the best way to think about the bus is that I had a bunch of wires. Like if my bus, which is 32-bit, it means that I have like 32 pins, right, to read the data, right? That's the best, most easiest way to think about it. And as you can look at those buses, that's the place where you plug in your memory, right? And not only memory, other devices, they all organize with a similar, like PCIe. If you want to plug in a graphic card or a sound card in your desktop, they also go into PCIe slot. And that's also a bus, essentially, right? So you plug it in there, and you see those parallel pins. This is the pins that can read data in parallel, right? That's essentially what it is. So multiple components can read data from a bus, but only can write to a bus once at a time. Each component has a tri-state buffer that feeds into the bus when not reading or writing, and the tri-state buffer drives high impedance onto the bus when needed. So whenever you see those things right now on your motherboard of your computer, hopefully you have a better understanding why it's organized the way you see it, right? And what really happens there. Okay, any questions about that? So this was communication medium. That's how we transfer the data. Let's look deeper into how those cells are organized. Because remember, at the end of the day, registers needs to store somehow, right? We already learned how we can build some memory from transistors. Hopefully you still remember that. But it's nice to see how it's actually organized on a real silicon. So we talk about RAM storage cells, which stores each bit of the memory. So essentially, for storing a single bit, each row is made of essentially an array of storage cells, right? And multiple ways of representing the cells. So RAM cell is basically a gated latch that we learned before, and that's how it's stored. And then it's essentially one bit is not enough, so we have to organize multiple bits, and we want word select logics that determines which bits to read and write and what to send there. So that's a schematic organization of such a circuit. Are we going to study about south-north bridges? No, Quentin, sorry, that course is not as advanced. That's more for like if you want to learn about south-north bridges and the specific, you would need to take some of the engineering courses that specifically look at how it's exactly organized. Remember, in CS, the focus is always on fundamentals, right? So things can be implemented different ones. So whether something is called south and north bridge is not really specific or fundamental, if you ask me. But if you want to learn more about how things exactly done, there are some interesting engineering courses you can take in computer engineering department. Sounds good? Yeah. It's not exclusive. Like there are certain fundamental things you cover in CS courses, and there's something interesting stuff you cover in engineering courses. But they're a little bit more advanced, so you usually take them in your third or fourth year. Okay, so now let's talk about SRAM, or static random access memory. And there are other types of memory, DRAM, SDRAM, VRAM, and all of that. I'm only going to talk about DRAM a little bit. By the way, the material I'm going to cover, that's the part that's going to be different from the lectures from previous years of this course, because my research area is on memory, so I want to give you a little bit more sense of what it can be. So I'm going to give you a little bit more details here. Hopefully it's not going to overwhelm you. But first we talk about SRAM. Usually that DRAM is not covered in the second year class, but hopefully you like it and you would understand it a little bit more. So asynchronous SRAM interface is an example. This part is still covered as in all traditional classes as well. So you had an address and bit, and you had read writes, and you had the data output, And that's essentially the schematics of it. There's nothing really complicated here. And this is the timing waveform. So there's an address coming, there's SRAM read, and there's SRAM write, and write takes longer. So essentially SRAM reads brings the data from SRAM, and essentially the write gets the data to SRAM, right? And that's how the waves are organized. Previously, how we look at other things. So reading and writing of signal takes time. So to make sure things are read or written correctly, we must control the timing carefully. So that also goes back to frequencies. Remember, when we think about CPU, I think I mentioned to you, when we thought about LUs, they operate at a certain frequency of their waveform. This is the minimal timing that allows me to reliably sense the change into your circuit, right? And essentially it's the same story here, right? The operations, the changes of the value starts much faster than the standard time, but I need to make sure it's done reliably. So that's why there is a fixed latencies that are associated with SRAM. And again, you're gonna see that there is a latency associated with the cell itself. And when it's used for register, it's optimized to be 1 or 2 cycles. But when you use it as a part of other data structures, it might be slow. So one thing not to get confused, remember, SRAM is a technology. A technology can be used to build different data structures, right? Similar to latches that we learned before. You can build registers out of you can use cache, you can build caches out of it. It doesn't mean that the latency is going to be the same, right? So this is one thing I want to really understand. So don't get confused because say, sometimes people confuse caches and SRAM because caches typically build out of SRAM. This is 2 different things. One is a technology. The other one is an abstract data structure that you built to be real using this technology, right? But it has its own design complexity and latencies and all of that. Okay, memory versus registers. So memory houses most of the data values being used by a program, and registers are more like a local data store, to be honest, meant to be used to execute an instruction. So remember why I really need it to be that fast? Because when I do an add, I want 2 registers being readily available. So as soon as I'm ready to do an add, I want both parameters to arrive at the same time. Again, if my add takes 1 or 2 cycles and my register is going to take 10 cycles, that's going to kill the whole purpose, right? I'm going to forever wait for these 2 parameters. So I need this small number of these local data stores that can supply data very fast. Registers are not meant to host memory between instructions like scrap paper for calculations, right? It's not something for long-term storage. You're going to see that registers use in and out. You don't really store anything for too long. So you're soon going to use assembly language. You're going to see how you use registers, and you need to keep track on what's meaning you assign to this register in this context when you're going to write your manual assembly language, right? When you write programs in high-level languages like in C, C++, someone will do it for you. That someone is a compiler that would do so-called process called register allocation. But you write your code poorly in certain way, then you might have not enough registers, and you'll have to go to main memory instead of register or cache, and then your code is going to be much slower. So this is why understanding hardware is very important, right? Because you can run your code much smaller. Yeah. Well, if you're using something like Python, then forget even worried about that. It's so slow. So all these hardware effects, it doesn't really matter because it's interpreted. So it's like it's thousands of X slower than native execution. So don't worry about registers if you're using Python. You're using C or assembly, that's where you worry about it because you run code really efficient. Exception is the stack pointer register, which is sometimes in the same register file as others. So a lot of things you may have heard about, like exceptions, they handle through the registers as well. Okay, any questions so far? I'm going into a lot of detail because I think it's very important when I think it's hard to make predictions about the future, but if I make predictions about your, next 5 years as a, CS, students, if you're going to worry about performance ever, you're going to mostly worry about memory other than CPU, because CPU is very fast and optimized and memory is much slower. So usually when your code runs slow, the first suspect is memory subsystem. Okay, so another memory technology is DRAM. So DRAM, which stands for Dynamic Random Access Memory, has a differently built cell. Its cells are built off of capacitor that charges states indicates a stored value, and whether capacitor is charged or discharged indicates the storage of 1 or 0. So it's one capacitor, one access transistors. This is in contrast to SRAM cells that might have like 6 transistors used, for example. There are different implementations, but there are multiple transistors used to store SRAM cell. So there are pros and cons in DRAM technology. The pros is because it's only one capacitor, one access transistors. It's much smaller, right? So it means they can get much better density. It's also much cheaper to build because there are way fewer transistors. But the big downside of it, that it leaks charge over time. So it has the RC path from which the charge gradually leaks. So if I don't somehow to get charge back periodically to DRAM, it's gonna all goes to ground zero and everything will be zeros in your DRAM, right? This is why DRAM goes through a periodic operation called refresh, where you supplies the charge, right? So DRAM cells loses charge over time. That fundamentally leads to a problem that they need to be refreshed. Okay. So in the next part, we're going to talk about DRAM in more details. Any questions before we go into DRAM about SRAM? Oh, very good questions. How often does refreshing happen for DRAM? I like these questions. So the short answer is that's a timing parameter that's specified in specific specification for the DRAM. So when we talk about DRAM, it's a generic term, but there is a different generations. There's DRAM 2, DRAM 3, DRAM 4, and they have different frequencies. Each of that specification has a manual where people, designers that build DRAM specify the timing parameters. And among these timing parameters, there is something called refresh rate, how frequently DRAM is refreshed. If you're using a typical laptop and you didn't, do anything fancy with it, if it's a typical Windows laptop, then you're probably refreshing every 64 milliseconds. If you're a Mac user, I had bad news for you. It's probably refreshed more frequently. This is because Apple, there was a problem several years ago. I think the research group I was part of when I was doing my PhD published a paper showing that you can flip bits in memory pretty much at your discretion, right? And you can flip bits in someone else's memory and steal information doing that. And people when this problem arises that was affecting all DRAMs used in all laptops and desktops, different companies goes for different solutions. So I've heard that Apple's solution was just to increase the refresh rate. So if you're using Apple, you might be having 16 millisecond refresh rate, unless they figure out something better. But that's the typical latency, something around 64, 32, 16 milliseconds. This is the period after which most cells might lose their charge. So you need to make sure that every piece of memory, and think about it, it's a non-trivial operation. Your laptop might have 16 gigabytes of memory, right? And I need to refresh all of it, no matter whether you use it or not, every 64 milliseconds. Right? So that's part of the technology trade-off. Okay, so DRAM random access memory. So obviously it's memory, so it stores information of that form, right? So that's what it fundamentally does. And its API, as I said to you before, is a read and write operation. So read has an address, right? And it stores in some register, and write has an address and a value. And accessing any location takes the same amount of time. That's the beauty of DRAM. That's why it's called random, similar to SRAM. They're both random. So they allow you to take the same amount of time to do it. Before I answer Sam's question, my question to you guys, why random access is so important? Why we want to have any location takes the same amount of time? So I'm expecting. Yeah, so Terry said consistent performance. Yes, imagine you're a programmer. Soon you're going to write assembly code. Again, I'm just reminding you that the peak of this course. Imagine you would have to worry that depending on which location in the memory you happen to go, it might go slow or fast. That's a nightmare, right? Because your code randomly mapped by OS into different locations of memory, and then your code can go either faster or slower. That's something I don't want to deal with. Sometimes we have to deal it. You're going to learn about it in advanced grad level classes, but usually you don't want to worry about this. Okay, so hopefully that you understand that answer. So Sam asked a very good question. Does this make DRAM more power hungry? Absolutely. So DRAM is very power hungry. In fact, memory subsystem, especially DRAM, takes as much as 30 to 40% of all the power and energy consumed by your computer. So it's the most power-hungry component, except of maybe a graphics card. If you're really actively into gaming and you're using your GPU heavily, then that's going to consume a lot of power as well. Although that graphics card also going to have plenty of memory, so most of the power consumed in GPU is also going to be because of memory. But that's going to be a different type of memory. Okay. Any questions? Okay, Terry has another question. RAM takes the same amount of time for any index, but for register, this is not the case, right? No, SRAM is also, we try to organize it that it takes the same amount of memory. That's part of their design of the register file and cache. We're going to organize it so the latency is going to be the same. Again, to avoid the nightmare of dealing with variable latencies. It's a hassle for the programmer, it's a hassle for the designer, because if I'm going to build a chip where cache can generate me different latency within the same layer, I need to buffer this somehow. I cannot expect whether it's going to take 4 cycles or 6 cycles, right? So dealing with random latencies is very painful, right? Usually you need to provision for the worst case. Okay. Does it answer your question, Terry? Okay, good. So let's move on through DRAM. So the data needs to be constantly refreshed. And as Sam already pointed out, that's going to be very power hungry. So essentially, when several years ago, Apple made the decision to deal with the so-called raw hammer problem, that's what we discovered in our lab, that leaks information leakage through DRAM, the solution was to refresh more frequently. Who is paying for that? Your battery is paying for that. So if you're on a battery not plug into the power, your battery are going to lose power faster. Okay, so it's not for free. So not all people were happy with this solution. So DRAM is used pretty much anywhere: the cell phone, laptop, mainframes, like everything. It's like all the main memory technologies right now based on DRAM. There are 3 major manufacturers that are still alive. It used to be way more, but the competition is stiff. So essentially, we had Samsung, Micron, and Hynix. This is the 3 major companies that manufacture DRAM right now. There are some other smaller companies in China and Europe, but they're really tiny. They don't have a big market share. So one question you may ask, why we pick this technology? I know that you don't know about any other technology. You tend to associate memory and DRAM pretty much as synonyms, right? Because you've never heard about others. I can tell you there are like tens, if not hundreds of different technologies people consider, and they failed one important test. They failed the efficiency test, and I'll show you the trade-off. So essentially, one big part to answer these questions is to understand how important is memory. So let's imagine there's a trivial program here written in a pseudocode where you read the data from memory twice, then you add up and write data back to memory. One thing important to understand, there's a processor in the memory. And as you read the data, the data comes from memory to processor, right? You put it in there. And to run a simple add, you run 4 instructions and 3 data accesses. Why is it important to understand it? You should get a feeling that the data accesses is almost as frequent as instructions, right? But so it tells you that the memory is equally important to the processor just from that alone. But to make things worse, memory is much slower than the processor. So there are factors that affect the choice of memory. I'll just bring 3. There is actually, when I talk to people at Micron or Samsung, there's about 10 different factors. I don't want to overload you, but that's the main factors for you guys as the users. It's speed. So it should be reasonably fast compared to processor. It's capacity. So I want large enough memory to feed my programs, and cost. It should be cheap, right? Like no one's going to buy slightly faster memory for like 3x increase in price, right? And that's what would happen if you had issues with density, for example. There are other aspects like reliability, fault tolerance, but I'm not going to go into that right now. Okay. So DRAM got lucky. So if you look at things you at least heard about or learned in this course, there are flip-flops, SRAM, DRAM, flash, and disk. Hopefully all of that you've heard about. And there's a trade-off curve here. On the x-axis, we had access latency. So going further here increases the access latency and the cost. DRAM happened to have a nice sweet spot in the trade-off spectrum. So there are tons of other data points in different places, but DRAM happened to have a very good trade-off point. It has a decent access latency with a very reasonable cost that make it a very favorable technology to use for main memory. And it is the main technology for the last 30 to 40 years, I would say. And people want to get rid of it. Actually, right now, DRAM coming from the existential crisis because it doesn't scale anymore. And there are all these problems with it, but there is no like a technology that would easily surpass it yet. Does this graph relate to how memory is in the middle of the hierarchy? That's a good question. Partially, yes. So it kind of explains you why we had different things in the memory hierarchy. Remember, there are hundreds of other data points here. You just doesn't click with you, so I don't bring them. Those are the other data points that exist, and they exist because they take some important part of the trade-off spectrum, right? Like, for example, disk is here. Its access latency is terrible, but it's cheap, right? So it is there because of that. And remember that things to get into this graph and to find your place in this competitive space is very difficult. The last thing that probably happened in your lifetime, because DRAM was invented before most of you were born probably, was flash. So when I was a child and was programming my first old computer, flash didn't exist as a technology. We had DRAM and then disk, right? And it was a nightmare when something doesn't fit into DRAM, and then flash technology came up that came with a cost comparable to disk. If you look at SSDs right now, right, then they are more expensive than disk, but not dramatically. You can afford it, right? And it has much better latencies, right, and power consumption. And the main important thing for the users of your laptop, it doesn't have this magnetic thing rotating all the time, producing tons of noise and heat, right? So it allows you to drop your laptop and hopefully it's still alive. If you use the older laptops, like the first laptop I used myself was in 2002. And they had hard drives. You drop it once, when the computer is active, you're done, because the magnetic thing was spinning and it drops on the floor, that's it. The hard drive just locks. So it's like they don't have any shock prevention in these early laptops. Yeah. Any questions? Okay. So one question you can ask is DRAM fast enough? In fact, don't think it's a dumb question. Like I got that when I was a grad student, I was asked, one of my friends at Stanford asked me that question. He's a systems guy, said, why you architects can build DRAM, much faster? So right now, a typical latency is around 50 nanoseconds. Is it fundamental or are you just lazy designers? So why can't you make it faster? And there are fundamental reasons for that. And the answer, I'll first answer it from a systems perspective. Is it fast enough? And the answer is not, it's not fast enough. Why? It's because if you had a chip of 3 gigahertz that can execute 2 instructions per cycle, that's a typical Intel chip. In 50 nanoseconds, I can execute 300 instructions. So remember I show you a small piece of code. Then for 4 instructions, I had 3 memory accesses, right? And the problem is for 300 instructions, I can only handle 1 memory access. That's where the problem is. Essentially, my processors, as you know now, can be multi-core. Like the i7 is going to have 4 cores, despite its marketing name i7. It doesn't have 7 or 8. It has just 4 cores. So that's just a way to cheat. By the way, the frequency you see on it is actually not a real frequency. All manufacturers right now cheat. So the frequencies, the nanometer process, everything is cheating. So when Intel says 7 nanometers, it's not real 7 nanometers. When they say 3 gigahertz, it's not really 3 gigahertz. You would need to run through the detail of the spec to know that's a marketing number they use to sell more, but they cannot sustain the old frequencies they used to have before. It's like a marketing term. So remember, 3 gigahertz is just an estimate, right? In reality, it probably runs around 2 gigahertz. Okay, so the problem here is with 4 cores, I'm going to generate, 4 more, right? And then I potentially need to, each of them might generate us more requests. And these independent programs running in each core, each is going to ask me to run even more requests, right? And hopefully your DRAM is at least parallel, so it's not going to serialize each of these requests. It might or might not, right? When you see those things here on DRAM chips, I'm going to talk about them soon. They're there for a reason. There's a reason why they built to have 8 of those. And that's something I'm going to cover in the second hour of our lecture. Oh yeah, I've seen people complaining about 40 nanometer scam. Yeah, like it's all not real. So whenever someone tells you 10 nanometer, 7 nanometer, I think there are 2 companies that produce circuits right now at a huge volumes, TSMC and like Global Foundries. A few others exist as well, but they are smaller. And yeah, so when they tell you something like 7 nanometers, it's at the best something like 16 nanometers. At some point, they struggle to scale the nanometer process. So, and they start to use new materials to compensate for the speed, but you wouldn't buy a new chip that would be the same type of nanometer process because everyone likes smaller because smaller means faster. So they come up with a scheme that name things in a way that would sound appealing to their users and consumers to buy it. But it is not really that small. So Ivan is asking, how can you just do that? Well, it's a marketing term. So it's like if you carefully read what 7 nanometer was, they use it in quotes, and there is even a quote like say, Intel 7 nanometers is different from TSMC 7 nanometers because they cheat differently. So they cheat different amounts. So the size is actually not equal. So when you buy 2 7 nanometer devices, it depends on whom they're coming from. People in the industry do understand the nuances, but people usually don't. Yeah, the AMD use TSMC, right? So AMD chips saying they use 7 nanometers. Their 7 nanometers might be actually worse than Intel 10 nanometers, but I'm not picking the sides here. I'm just saying they all cheat differently. Do you have any advice of being able to tell which specs of a processor spec sheet are worth looking at? So very good questions, but that's not something I can cover easily or quickly. There's a lot of articles on that and benchmarking. I can tell you that right now, AMD chips are actually doing very well. They're very competitive. For many, many years, Intel was dominant in the area, but now AMD chips are very competitive. Like all the desktops are built for my students, for my graduate students to do research are based on AMD chips right now. Performance per dollar, they are the best right now, in my opinion. How do they argue that it's 7 nanometers? So that Sam is asking. By the way, there's a break right now, but I'm happy to answer the question. So stay in the line if you're interested to listen for answers. How do they argue that it's 7 nanometers? So around 10 to 15 years ago, when the scaling of something called Dennard scaling, again, that's not covered in this course, but there is some scaling mechanism that drives this industry for 40 years, stopped because of the power issues. They need to survive somehow. So they started to use naming conventions that when you use a new material, but that look like as if I would scale from 10 to 7, I would reach the same performance, then they use the same name. So they make their circuit faster, but it's not necessarily smaller. They just, instead of regular transistors, they use FinFET technology, and that makes the material still same size, but runs faster. So it's the same as with frequency. When they tell you 3 gigahertz, it's by Intel, use so-called Pentium rating. So they take the performance of the old Pentiums, and that's used as a reference point. So if you're 2x faster than 1.5 gigahertz Pentium, that makes you 3 gigahertz. But reality, you might run at a much lower frequency. So Andy Juan said 10 nanometer class denotes chips made using processor technology between 10 and 20, and that's actually very correct. So there's a whole range. The typical one would be around 16 nanometers, really. I don't think any 10 nanometers are really 10, to the best of my knowledge. Maybe I'm wrong. Someone's not cheating, but as far as I know, they're all cheating. Can we watch the AMD GPU release instead of having a class? Oh, guys, sorry, that's in your spare time. Okay, so now it's a time to take a break, and I'll see you at 12:10. See you soon. Okay, so let me answer a few questions here. For CS students, will be there a huge difference between AMD and Intel CPU when doing programming? I've heard that Intel CPU is more stable or supported or something, so I would like to make sure. Not only for CS, but in general, for most people, there's not going to be a big difference in performance, right? Unless you do something very computationally intensive. Intel likes you to believe that AMD is less stable or something, but it's not true for many years. Another question, and again, this is based on my experience and based on the benchmarks that I run with my students. Before buying anything, we do run extensive benchmarking. In general, if you hear a claim from someone, remember sometimes companies are paying journals and websites to publish certain information. Always try to look for more independent benchmarking happening. Each of those things has independent benchmarks. Another question is, are we learning higher level of organization this week and last week, since we are not getting into details of LU and memory design? We're going high up the stack. Remember that first slide that I showed? So we're inside the processor, so we're learning about how things are organized within it, but we're not going to go into any more detail of LU, right? So that's it with LU, right? So today you're going to learn about memory, then you're going to learn about control flow next class. And after that, we're going to be spending 3 lectures on assembly language. So you're going to only go in high up the stack. I think you go as low level as you technically can for an undergrad class at this point. So we went all the way to physics and circuits, right? Okay, let's continue. And again, request to all of you, please turn on your cameras if you can. Let's continue. So the main issue, as you see, the latency, and you need some parallelism to compensate for that, but it doesn't solve all the issues. Okay, again, some advanced material from their grad level computer architecture, so hopefully you don't mind. So I want to go a little bit deeper than you're typically going to see in most CS classes, but since I'm a computer architect, it's important, in my opinion, for you to understand what happens here. So this is your typical DRAM chip, right? This is your processor. So this is what happens if you actually use some advanced, technologies to look inside of it, right? That's reverse engineering of DRAM, because remember, a lot of details about DRAM is covered by, proprietary patents by different companies like Samsung or Micron. So essentially, this is how it looks inside of it. So essentially, those pieces are not randomly there. They're called banks, and they're there for parallelism, right? To allow you to read from multiple parts of DRAM at the same time. So if you look inside of an individual bank, what you have there is a structure called the mat. And essentially a mat, the best way to think about it, is a 2D array of memory cells, right? So you see how many layers of hierarchy. There are different, you can have multiple different chips. Chips have different numbers of banks, and within banks, there are multiple mats, right? And within mats, there are multiple cells. There's a reason why I built it. I'm not going to go into that, but this is how it's done. And the way the data is read, there is a word line driver that tells you which word to read. But within this word, you only need certain beats. And there is a beat line that allows you to read the specific beats you need. And there is a structure called sense amplifier that essentially drives the charge for you to read from the row and then fix the charge. Remember, one problem with DRAM, because it's based on the capacity, whenever you read or write, it's destructive. The data is lost. So you need to reconstruct the data every time you read or write. And you want to amplify the charge when you do read operation. Yeah, I'm not going to go too much over it, but that's a very good description how DRAM cell is organized. So how individual cells look like? So again, remember, from a very trivial high-level perspective, memory cell is just some entity that has a state of 0 and 1, right? This is how you want to think about memory if you don't do anything special about it. It can be electrical, magnetic, mechanical, right? Like the different ones. DRAM uses capacity, so it's electrical. And essentially, the best way to think about capacity as a bucket of electric charge, remember coming back to the early lecture, so you can charge and discharge things. This thing here, this is just for illustration purposes. There's a voltage level indicator for a few next slides. Remember, this is not part of the design. This is part of the design with the capacitor, not this. So for example, when things are charged, you can have certain value. When things are discharged, you might have a different value, right? So essentially, DRAM chip contains billions of capacitors called cells, right? It's a huge entity with tons of capacitors in it, right? Each of this tiny cell, this is a bucket of charge, right? And the things, as you can see here, the distance to different values can be variable, so that brings some complications on how to operate it. So the way to conquer, so you see, going from here to here would have very different distance, right? And we'd want same latency, right? If you say something is same latency, that either you make it worst case, and in this case, it might be so much worse than you don't want to do it. So to deal with the latency, we slice things. So I never need to go too far, right? So this is why I had banks. Banks are to reduce the latency. Within the same bank, I'd never need to go further than this, right? Within this. So all these things, but there are still the questions like how are you going to go something further with something closer. So there are some challenges with DRAM, which again, I'm not going to talk about that. So it's one changes is there can be some weak cells. And essentially, when you manufacture this thing, unfortunately, not every cell is identical, and weak cells would dominate the latency. So reality is that some cells, when you build up it, remember in the first lecture, I was showing how things are manufactured from silicon, right? So when things are manufactured, unfortunately, they're never going to be 100% perfect. There are going to be some small cells and some large cells. So large cells, they happen to, it's harder to charge them, but they lose the charge slower. But the small cells lose the charge quicker. It means I need to optimize. So they're faster to read, but they lose charge faster. So that creates some challenges. And again, destroying is another problem. So sense amplifier, that's the circuit we use to read the data based on the voltage. And essentially what sense amplifier does, it amplifies the charge. So when you read the cell and the charge goes down, and in some cases it's higher than half and some lower than half, sense amplifier amplifies the charge. So amplifies the difference. So it makes, something that's closer to, bigger than half, closer to the value that would be full, and something that is smaller than the half, closer to the absolute. So it would be detected as 0 and 1. So it just fixes the loss in charge in the right direction. So essentially you get either maximum or minimum. That's what sense amplifier does, right? It adds delta to the charge, and that's a stable state. Okay, so we covered a lot about DRAM. Let's talk about some more fundamental things about how you would optimize the code and how you deal with long memory latency. Hopefully now all of you get a sense on how slow is memory, right? A typical request is around 50 nanoseconds, and that's very relevant for like 10 years. Yeah. So essentially most processors spend most of their time waiting, often for memory. So that's a main problem with existing CPUs. They do spend a lot of time waiting for something to arrive to do compute. Compute is so fast, but they're bottlenecked by memory. So this delay, because of how slow the memory is, got a name. It's called memory wall. So what the memory wall means, it means no matter how fast my processor is, if memory is too far and too slow, I spend so much time waiting. So it doesn't really even matter whether I execute fast enough, because essentially I can execute hundreds of cycles on my CPU before the data arrives. If the load, like if I had a execution and I had a load instruction and I need to wait for 300 cycles, then it doesn't really matter how fast is my adder, right? Because adder doesn't add a lot. Okay, as a result, there is a law that's called Amdahl's law that you're going to hear in a lot of other courses potentially, that tells us conceptually how different things are optimized. So Amdahl's law tells us memory access time is an aspect of performance that has become increasingly important. So essentially what Amdahl's law formula is, it's a statement in computer architecture about system performance. So essentially the statement is that performance gain in task achievable by optimizing a subproblem is limited by the proportion of time spent in that subproblem in the unoptimized task. So essentially, if I had a piece of the data that was only 20% important in an optimized task, even if I make it 100x faster, I cannot speed up my applications more than 20%, right? That's a very common reason about the speeding. So sometimes people get into this mode that I want to speed up to infinity, and certain things just don't worth optimizing if it's costly. So if you only spend 100 of your time doing a task A, even if you reduce time requiring for A to 0, you'll only save 1% of the runtime. This is why if you are a reasonable systems person, the first thing you do before analyzing every application performance is a getting profile of how it runs and where the time goes. And then you optimize based on where the bottlenecks are. So essentially conclusions from Amdahl's law is you focus your optimization efforts on the tasks that consume the most time. I put yourself here a formula on how Amdahl's law to apply to parallelization, because that's the most common use case it's used for. So essentially what that formula shows, it shows you how much you can speed up things if you parallelize with multiple processes. That's because that's the most common case when people try to speed up things. There's multiple cores, multiple threads. So there's only one assumption here. There is a portion of the code that's parallelizable, right? Like it's written in a way that it can be run in parallel. And there is a certain portion that is sequential. So essentially there is a part of the code that is 1 minus f. This is the part that runs sequential. So no matter how many processes you have, you can accelerate that part and increase the total speed up, but you never can go faster than this. So even if you bring the number of processes to infinity and that becomes 0, you're never gonna go faster than 1 minus 1 over f. So for example, if the sequential code is 10%, right? So that so essentially then 1 minus f is going to be 90, then you're going to be somewhat closer to good speed up. But if you're actually going to have the it's the other way around. So it's parallelizable fraction. If non-parallelizable fraction is 10%, then this is 90%, and I don't speed up things faster than 1 over 90%, 0.9, which would be 10 over 9, right? So I can barely speed up by 10%. That's the common sense thing. I really need to increase the amount of parallelizable fraction of the program or optimizable in any other way to see a reasonable speed up, right? This is the reasons why if you want to optimize the code, your first step is to get a profile of your code, how much time is spent in each function of your code, and how hot it is versus how cold it is, and then optimize the hottest code. So maximum speed up is limited by a serial portion, which is called the serial bottleneck. Okay. So as a result, Amdahl's law tells us that the memory access or parallelization, all of these optimizations are just one aspect on performance, right? And if your memory access is serial, which is in the way we describe it so far, it means that it doesn't really matter how fast I'm running the rest. I'm just bottlenecked by the memory because it becomes a serial portion. Okay. People were realizing that the problem with memory exists as early as end of 60s, beginning of 70s. And they come out with something called the cache as a structure that tried to create an impression that the memory is located closer than it really is, so you run faster. So what's the key idea behind caches? The idea is that every load to memory fetches more than just the value it's loading. So if you've heard about caches before, you would know they operate at a certain granularity. That granularity is called a block or a cache line size, right? So whenever you read 4-byte or 8-byte from memory, actually processor brings more data from memory. And this is the reason, because there is an expectation based on many, many different programs written by different people, is that the data you read now and the data you're going to read soon is going to have some nearby data that would be useful as well. So if you read more than you need. Why is that a good idea? Because the reason is because the bus is already implemented with a certain width. It means that reading 4-byte versus reading 32-byte is pretty much the same speed, right? You're anyway going to burn that. So it seems like it's almost for free. So essentially, reading it cheaply is not that expensive, reading more data. And that means I can read more data. And if my guess is right, I can benefit from it. So essentially, the very big idea that in my computer architecture class, I dedicate the whole hour. Here, I can only spend a few slides on it. But I really, if you're interested in computer architecture, I encourage you to read more about that. This is a locality thing. Locality has two major forms, spatial and temporal locality. Usually the way I tell students about the locality principle is when they actually especially in smaller classes where you had like a senior undergrad class, like 4th year, or grad level class, there's usually about 20 students in the room. And there's one easy observation I made over the years teaching different courses. First of all, there is so-called spatial locality. What does it, of students in the room, what does it mean? It means that the students like to sit near the same students every single time they're in the lecture. And right now you're not doing that, but probably you've seen this before, right? So the people tend to cluster and sit near the same people all the time. And so that's a spatial locality. It means that if I know that this guy is here, there are probably these other people sitting near him or her, right? A second observation I made is a temporal locality, which is kind of trivial. Like if you had a schedule on the classes, so with a high probability, if our class is at 11 a.m. on Wednesday, so with a high probability, I know you're going to sit on the same place watching, the class, right? If you like to attend classes online, right? So essentially, that's a temporal locality. So if I see you on Wednesdays at certain time, last week, there's a high likelihood you're going to see you again, right, at the same time in the class nearby. There is also another aspect of temporal locality, which means if I do see you in class at 11:30 and the class is 2 hours, there's a high likelihood that 11:40 and 11:50 I still see you. So this is two aspects of temporal locality. So briefly speaking, one is about spatial aspects. So if I bring something nearby that's helpful and it's cheap, and temporal thing. So if I see something frequently, right, there's a high likelihood I'm going to see this in the future. So if I see something recently, it's probably better to keep it close because I may ask for it again. So if I ask some memory to bring, it's better not to forget that information and keep it closer because I might ask for it again. This is a big idea in computing, multi-billion-dollar idea. It's one of the things that speeds up performance dramatically. So essentially, if we use something recently, we're likely to use it again or something near it. So something near is spatial locality, soon temporal locality. Okay, so what are the examples of the code you wrote? So when you iterate over an array sequentially, then you exhibit both temporal and spatial locality, right? Because you go through the same elements multiple times. You get spatial locality because if I access element AI and then I access element AI plus 1, it means when I first ask for that element of the array and I next the next one, they're co-located in the memory, usually sequentially. I say usually because you might allocate memory differently, but usually it means spatial locality. And if you iterate over that loop multiple times, you get some temporal locality. Executing code also exhibits both temporal and spatial locality. But accessing items from a dictionary does not, because the items in the dictionary may be not close to each other in memory because you can randomly access different things, right? Linked list and other dynamically allocated structures that you hopefully already learned can also cause locality problems because their memory might not be allocated sequentially. And people do a lot of optimizations to fix this problem. Okay. To learn about caches, unfortunately, there is a lot of terms you would need to learn. So today, I'm going to define a lot of these things informally so you can still get the idea. If you want the formal definitions and everything I'm going to talk for the next 30 minutes, you would need to go and look at your textbook and read about that. And again, remember, this is just for your own benefit to learn more. Like in all the quizzes, exams, I'm only asking you whatever I present in the class, right? I never ask you the questions that were not covered in the classes, okay? But if you want to understand things more formally, there's a good place to go and read in general. Okay, so address, tag, block, set associativity, hit rate, all that might sound cryptic for you right now. I'm trying to show you some examples on what is what. Okay, so some informally defined terms. First of all, the cache, the best way to think about it is the very small subset. Well, when I say very small, still bigger than registers, but a small subset of the data that we believe can be used in the near future. So instead of going in for memory and paying, I don't know, 300 cycles, we store it in some smaller SRAM-based storage. It's going to be slower than registers, but it's something on the order of 4 to 10 cycles, right? So that small thing is something we put in the processor itself. And if it's really near the processor, it's usually in the kilobytes. If it's a little bit further away from the processor, it's in megabytes, and there's a trade-off around that. So this is cache. The question is how to organize the cache. And you would be surprised, there are students applying to grad programs sometimes, and they learn caches, and they ask very basic questions about caches, and they don't really understand because they just memorize things. Don't be like that. Always question the key principle. First of all, the cache, it's not just the data itself, because it's not having all the data in the memory. It has to have some information somewhere to tell you what is in the cache and what is not. Because when you ask for the data in the memory, you first look in the cache, whether it's there. And I need to have some meta information to tell me whether the data is in the cache or it's not. Because if a cache have, say, only 16 kilobyte, I cannot have more than 16 kilobyte of data in it. So a lot of data is not going to be in it, right? So there are different ways you can store that meta information. And that's why the different types of caches exist. One is a direct map cache. So essentially, direct map cache is very simple. You look at the address of the memory, and then each memory has a one-to-one mapping. So it means that for each address, it's only in the one block of the cache it can be there, and nowhere else, right? It's very easy mapping scheme. So you look at your address, you say, oh, if you finish with all zeros, that you mean, like you say, if you had, say, 4 blocks, then you only can have 4 blocks in your cache, right? Then you look at the last few bits of your address, and then that tells you whether it's in the first block, second block, third, or fourth block, right? Only one location. That's a direct map cache. And N-way set associative cache is the cache where you might have multiple blocks in the same address kind of located. That helps because it reduces certain type of common issues with caches. We're going to talk about that with some examples. You're going to see it. Another cache called fully associative cache that has a complete freedom. Any block in the cache can be anywhere. It's called fully associative, and it's very expensive to have it. So essentially, memory address, remember what is memory address? Whenever you load or write something from memory, you always had a memory address, right, where to read it from. That's used as a pointer to where to store the data. And different memory addresses may have a hashed point to same or different sets. Okay. So each load fetches an entire cache block, not just a single value. That's one of the key principles behind caches based on spatial locality. So if you want 4 bytes, I'm not going to bring you just 4 bytes. I'm going to bring the full 64-byte cache line this 4 byte happens to fit within, right? And the size of a cache block is dependent on the cache. Most caches you're going to deal right now is 64 byte in their cache line. Pretty much every cache is I know. There is some difference if you use GPUs, but otherwise it's 64 byte. So essentially a block is just a set of consecutive words with closely related addresses. So for example, if you had array 0, array 1, and the array is 32-bit array, so you had 4 byte, another 4 byte, another 4 byte, another 4 byte, right? And you had 16 of those values all together. So why do we fetch a whole block? I hope you already answered that question because of spatial locality. So how we identify the bits that are needed in the address. Many of you have heard about masking, but I will just repeat for you again, for those who don't know. There is a principle called bit masking. So essentially you interpret a vector, a value as a bit vector, as an integer, and that should be interpreted as a sequence of bits, right? That's what you do. So what you take, you look at the address and treat it as a sequence of address. And the mask is the value that can be used to turn specific bits in a vector on and off. So for example, if I know that I only have 4 blocks in my cache, right? It means there's only 4 potential locations, right? For each 4-byte value to be stored in the cache. How would I store the value? Well, the most trivial scheme would be kicked all the bits except of the 2 last bits of the address, right? So what you do a mask with all zeros for the first 32 bits of the address, and then you keep only 2 bits at the end with ones. So I kill those bits because they're irrelevant to where you're going to map. And then you look at the last 4 bits. And if the last 2 bits are 0, 0, then you go to first block. If it's 0, 1, you go to the second block, right? If it's 1, 0, you go to the third. And if it's 1, 1, to the fourth. And it means that all other bits are irrelevant. So that example here show you 16-bit mask, right? So essentially what you do, you create this mask. You see all zeros F. That represents the last whatever 4 bits, right? And that represent from 0 to 15 all the values, and everything else is removed. Why? Because it's not needed to define what you're going to do with this value. So this bit mask is using for addresses. So let me show you how it works in the example. Consider an 8-bit memory address, which is byte addressable for simplicity. And essentially, this is your memory address, 10101010. And you might have 256 different addresses. Remember, oversimplify, like the real memory is in gigabytes. It has a much larger address, but this is just simplification. Imagine your memory is this big. And then imagine that we want to divide all these addresses in 8-byte subblocks, right? How many blocks are there? Well, you essentially can think about as being hierarchical. There's a block number and offset within the block, right? So essentially, this is your block number, right, of your memory. So the total memory, and this is block offset, right? So essentially, you can use different masks to just extract the block and the offset, right? So for caches, we want to mask out the top bits and keep the bottom bits, because the bottom bits tells us which block in the cache we want to go. For example, let's say we had a 32-bit address space. We need to find something called a tag set and the block offset for a direct map cache. What all these cryptic things mean? Remember, for me to know whether something is stored in the cache or not, right, I need to have some identifier. That identifies your address. So whenever I see your memory address and I know you're about to occupy some block in my cache, I need to know that you, not someone else, took it. So for that, I had an entity called a tag. You can think about it as an address on the door that has your name. So for that address, we use the top bits of your address because that identified the page, right? The memory page you would belong to, right? Essentially, right? There is also a set and the block within it. So essentially what happens in the direct map cache, we use part of the address as an index in the cache. That's the low order bits, right? The low order bits tell me you go into block 0, block 1, block 3, block 4. And the top bits are stored in the tag bit. That tells you, if someone else wants to come to the same block because they want the same offset, you know that they are conflicts, so you need to remove this guy and put the new guy. It also tells you whether the information you need is there. So for example, when CPU asks for certain memory, you go into the cache, you take the address, and you remove only the bits representing the tag. And you compare what you had in the tag in the cache. And if it matches, it means the data is already in the cache. And if it mismatches, I need to take this data out and bring new data in. That's called the cache miss. Okay, any questions about cache masking and address masking? You're quiet. I hope not everyone is lost. Okay, think about it as think about the cache as a bookshelf near your desk. So registers is, okay, so someone is fair saying it's lost. So we will repeat some stuff here. But I think about the cache as a shelf, you know, on your wall, and you have some books there, and there's only spots for 4 books, right? So whenever you request a book, you look at the bookshelf and you see what's written there, right? That's your tag, right? And you see on the tag that you had the right book. So if the tag of the book you want, the name, matches what you see on the shelf, it means tag matched, right? So if the tag matched, you just grab it from the shelf, read it, put it back to the shelf. If for a long time you had a book on calculus in your first year, and then you're done with calculus, right? And now you're starting to take OS class, you notice that that calculus book is taking space, but you always had to go to another room or the library for OS course book. So what you're going to do, probably, if you're smart about it, you remove the calculus book and you're going to put it to some other random place, to a storage, and you're going to put your OS book right now, right, closer to that. And it might take exactly the same position that the calculus book take. And the way you distinguish them, right, is by looking at the tag. And then you might 10 times you read this book on OS, taking it from this shelf. And then later, in some of your advanced systems courses, someone asks you a tricky question on calculus, and then, oh my God, I'm missing my calculus book now to read it, but it's not on the shelf, so I need to take the OS book off and put something in again. So this is essentially how it works. The number of spots is limited. I need to have those names for them to distinguish, okay? Any questions? Yes, absolutely, you're correct. There is going to be some algorithm. It's better to be simple because I need to do it in hardware, that it tells me which data is useless, which is useful, and we don't know the future perfectly. So it's going to be a heuristic, a guess, what's useful versus not. Right now, just don't worry about, think about, there is some heuristics that tells you what's useless versus not, right? And the cache is going to be managed using this heuristic. Right now, you're just trying to understand when the data is there, how I found it. Like the way I found it is by using the tag, right? So I need to do 2 things in the cache. I need to find data in the cache, and I need to place new data into the cache. So when I place it, I need to know where. And the where I define by a few last bits of your address. I just say, well, if you happen to end with 2 zeros, you're going in position 0. If you ended up with 1 0, then I go into 3rd slot. That's it. And it's true for everyone, right? So this way I know quickly where to look for certain books, right? Okay. Any other questions, guys, before I go into some examples on how caches work? Any other questions? I'm pretty sure others have questions. Please don't be shy. Yeah, so essentially you take the address, right? And within the address, there are bits that are dedicated to tag. And the other thing is dedicated to a block number into the cache. For simplicity, we assume the direct map cache for now. It means that every book has just one place on the shelf, right? If that's the case, then this few bits of offset tells exactly where your book can be located on the shelf. So imagine I'm a very picky person. I won't tolerate random books being in random places on the shelves. I want particular color books to be in one place, right? Think about there's only have 4 colors, so each color goes into one particular slot. Okay. Ivan, did it answer your question? So the offset is the part of the address, right? So we just decided to interpret the bits of the address in a way I described. The top bits tells you where, the main, whether that's this object or not. Yeah, so someone says we have register, cache, and DRAM. Registers is needed right away at the speed of the compute. Cache, what is likely would be useful very soon, and DRAM that was useful in some distant future, but still needed. So you don't want to keep it on disk. Okay, that's correct. Okay, so essentially what we're gonna do, some bit masking here, right? So what we're gonna do is those bits here, right? If you had a cache that has 16 blocks, and so we would need to have some bits associated with the offset within the block, and then there are also there can be bits associated with the set. Everything else is the tag. Okay, so don't worry too much about that. That's an automatic thing that happens in the processor, but essentially that's how the basic drag map cache works, right? So there is just one location for every block, and this is the bits I use for the address, right? So essentially, cache has some hashing function that decides where to move. The most trivial hashing functions is identity, right? So you take those bits 0, 0, and you map it to the first block. I just try to keep it simple. You can make something more complicated. So the next big thing about caches, remember, they are very small. They're much smaller than the memory they're caching from, so they cannot store everything. So if 2 blocks happen to map to the same value, they can be stored both at the same time. It's either one or another. So if I'm only had books of 4 colors and I require that each slot in my shelf of 4 colors can only take 1 book, then if I bring 2 blue books, right, then one has to go away. I cannot have 2 at the same time. Okay, so that problem caused a huge performance degradation of the cache operation. And I'll show you one example where we use direct map caches when there is no fix for this problem, and that's going to cause a lot of issues. So to avoid that problem, people implemented set associative caches. What does it mean? It makes my compartment for one color not have just one, but a couple units. So it means when I want to put a blue book, I might have a maximum of 2 blue books, right? There are 2 slots for blue books, right? So it means that if another blue book is coming, I have a choice which one to remove, but I don't need to remove, like there is more than one, right? So if you happen to have 2 blocks that come into cache frequently, and they happen to be of the same color, then I don't need ping pong them back and forth, back and forth. I can have both of them at the same time. So essentially a 2-way associative cache means I can store 2 blocks that happens to hash to the same location, right? So the best way to think about, I had shelf and I had compartments within shelves. So I allow a couple of items, 2 blue, 2 red, 2 green, and so on, right? A fully associative cache allows the total mass. It allows every color go in any location. It's completely flexible. So that's the difference. Any questions about set associativity? Okay. So the people that want to look at the formalities, this is the block diagram on how a 2-way associative cache is going to look like. So essentially, this is your memory address, right? There are top bits top bits here that represent the tag. There are bits that represent the set, and the bits represent offset within a tag. Remember, your address bits, some, for example, if you had 4-byte values, right, there can be byte 0, byte 1, byte 3, byte 4. The whole cache block has 4 bytes. So I don't need the 0 byte and 1 byte are going to be located in the same block, right? So I don't need, so the last few bits, I only store them for the offset within a block. And this item here tells me which compartment on my shelf I go. That's a set number. And if we had a block with just 4 sets, we had set 0, 1, 2, 3, 4 here. That means I need 2 bits from the address here. And the other are the bytes of the offset of the data. So what do I have here essentially? I have 2 bits here, right? I had 2 bits here, and the leftover 28 bits are the tag. And they are used to find whether the data is in the cache or it's not in the cache. Is this clear? So the tag is used to tell you whether that's the book you're looking for or not. The rest, these bits, are used to tell what is your place in the cache. And this is the actual data. That's what I'm looking for. And that is the tag. This is the name of the book. There's also an extra bit called validity bit that is here to tell you whether that's even used by someone or not. Because sometimes at the beginning, everything is zeros, right? So I want to distinguish that those are empty blocks I want to use. So that's called validity bit. And this is 2 ways. So in one set, I have space for 2 books of 1 color. So a set is a color, and ways are 2 spaces for 2 books. Okay, so tag tells me whether something hits or misses, right, by looking at the tags. And then here I use a maxis to, like if I find the data in one of these tags, here or here, right, because it's done in parallel, then if it's a hit, then I know which one it's a hit, and then the max will read me exactly the right data, right? Okay, that's a formal definition of it. Each cache has a finite size, so we can only store so many blocks. So we need to have a mechanism, as someone already brought up, to figure out what to keep in the block versus what's not. When we need to remove something, it's called eviction. Every time a load is performed from memory, so the block must be stored somewhere, and it means something has to be removed from the cache. Okay, how we choose what to evict? Ideally, we would like to kick out the data that we'd never see again because it's useless, but we don't know the future, at least I can't. So what we do, the next best thing, is we try to guess on the locality. We try to remove something old, whatever old means, right? And there are different heuristics that we use, such that least recently used or first in, first out, and a lot least frequently used, and some other heuristics. All replacement policies and caches are heuristics. They're not precise. They're just a guess about what might happen in the future. So the next few minutes, we're going to show a few examples on how the cache operates, but the detailed example how the block associativity and cache size affects the cache, you would need to study on your own on the reference I suggest. So let me go at least one example today, and we can cover more examples on Friday. So what we want to do right now, and you will need a piece of paper to do this, right, and a pen or like a computer, whatever you prefer, but you will need to keep notes. The first example I do with you, so you get how it works, and then there are a few more examples you can do on your own. So essentially, these strings of addresses, again, I specifically pick a small addresses, so you don't need to deal with other long addresses. This is the memory addresses you have, and we assume these are small numbers, right? And then hex, right? So this is, it goes all the way to, 55 here. The cache is direct map and stores 4 words. That's assumption. So we only had direct map cache. It means each block can only store it in one location, and it uses a first in, first out eviction policy. It means that here it's not very relevant because it's just direct map, but it's just some heuristic. Okay, how would I represent the fact that I had 4 blocks, right, in the cache? This is what I do, right? There's set 0, set 1, set 2, set 3. There are 4 blocks, right? Each of them can take a 4-byte value. That's an assumption in this experiment. So let's look how we're gonna process that. So we're gonna look at the address 40, right? And you can assume the most trivial hashing, which is identity function, right? It looks at the bits of the address. So here I can store 4, 8, 12, 16 bytes. So I look at the last 4 bits, and that tell me, because 4 bits represents 16 bytes, right, in the address. And then it tells you where I go. So if I had 40, you truncate the first byte and look at the 4 bits, and it tells me that block needs to go here. Is this clear to everyone why 40 comes here in the first block? That's a very trivial mapping function we use for simplicity, right? So then the question to you guys, where 48 is gonna go? Which block? Terry's saying 1, and that's not correct. And there are not that many choices left. No, it's not 40 either. Sam is right, it's in 2. Why is it in 2? Well, at least no one said 3, so it's not too bad. So I hope there was some logic in selecting 2. It goes here because you truncate the first bytes, and then you look at the address left. You're gonna have 8. So it means it's 8 bytes. So the first 4 bytes go here, the next 4 bytes go here, that everything starts from 48, from 8 needs to go to this block, right? And the next 4 starting from C, which is 12, goes to this block. Yeah, 47 goes to 1, that's correct. So this is how the mapping works. It truncates the bits, then it removes a few bits from the end as well, because they're the shift within the block, and whatever bits left, that's your set number. So you remove the top byte, then you remove 2 bits at the end, and whatever bits left tells you the set. So it's either 00, 01, 10, 11, right? So what happens when you go at 49 then? Would it also go into 2? Yes, first of all, regular assembly doesn't allow addresses like 49, but if that would happen, yes, it would go also into 48. But then you would only can store 3 bytes of it here, and the rest would go into the next block. We don't allow misaligned accesses, right? So we align, things needs to be aligned. But if you access 50, it would be here, right? So 49, 50, 51 all goes into block 2, block number 2, which is third block. Okay, let's continue. So when we get 4C, right? C means 12, right, in hexamal. So essentially it goes to the third block. Is this part clear to everyone? Okay, so then we get another 40, right? So we already handled this 3, get another 40. When we get another 40, that's already in the cache. We don't need to evict anything, we just read it. We found the address matching. I'm not going to show you the tag logic here, but we match. So that's a hit in the cache. And remember, so far, all 3 other ones were misses because the data was not in the cache. That was all misses. There's only 1 hit. So then we access 50. 50, because you truncate the first byte, has to map where 40 was. So 40 is kicked out and 50 comes in. And when I mean 50, it notes the value 50. It's the data that was stored on the address 50 goes into this block, okay? Then you get 58 and it goes here. It's direct map, there's no other place to go, right? 5C goes here. And remember, this is all misses. Then another 40 comes and oh my God, we had 40 before, but it was kicked out by 50 because we don't have set associativity. So 40 was kicked out and that means it's going to be a miss, right? Even though I've seen 40 twice before, I was not smart enough to keep it in the cache. I kick it out by my dumb policy and my dumb cache organization. So 40 is going to lead to a miss again. I'm storing 40 here. Then 60 comes. 60 has to map where 40 is. So it immediately evicts 40 again, right? That's how the cache is organized, direct map. And 48 comes, then 4C comes, right? And then 44 comes. Finally, this block is used. You probably noticed this block was not occupied until recently. And I would love to use it, but I was not flexible enough to use it. Then 40 comes here. And again, it's a miss. Even though I seen 43 times, I didn't make any right conclusions. I kick it out, and then I'm paying the price of missing. And then 60 comes again, 58. All of these blocks are missing because I never preserved them, even though I've seen them before, and F5C misses again. So there were a total of 16 accesses here, and only one was a hit. So what I remember here, despite our very good intentions of building a nice cache, a direct map cache might have a terrible performance. Like I give you some reasonable sequence of accesses with some locality, and I was not able to exploit it. I only get 1 of 16 happen to be a hit in the cache. I'll show you later we can improve it dramatically if we make a slightly better modification for the cache design. But in the interest of time, I think we're already over time. So we will do this in the tutorial. I'll go over a few examples. I'm also going to leave the animations with the slide so you can play with it and look how things change with different cache organization. Any questions? Okay, if no questions, then thanks everyone. Thanks for your patience, and hopefully you enjoyed learning about DRAM and memory. Okay, bye. Thank you, guys.